Hello friends, in this video we will try to understand the concept of differentiation for a rectangular function. So if you look at the plot of the rectangular function given here, we can easily see that this function is discontinuous at two instants of time, at t equal to 0 and at t equal to t naught. Okay, so this is discontinuous at two instants of time. So according to classical integral and differential calculus, we have studied that for a function to be differentiable, first it has to be continuous. Okay, so but the given function is discontinuous at two instants of time, and hence clearly this rectangular function is not differentiable in classical sense. But according to modern field of mathematics called generalized function theory, so this we can evaluate the derivative of this rectangular function by replacing the discontinuities with what is called Dirac delta function. So we have to replace the discontinuities with Dirac delta function. So we have discontinuity of we have a positive discontinuity of 1 at t equal to 0, and we have a negative discontinuity of 1 at t equal to t naught. So if you try to plot the derivative of this function, the plot will look like this. Okay, so according to this field of mathematics called generalized function theory, so we have to replace the discontinuity at t equal to 0 with a positive Dirac delta function, the plot of which will look like this. And at a t naught we have a negative jump because the signal is jumping from 1 to 0, and then we should replace that discontinuity with a negative Dirac delta function, and we call that the term inside the parenthesis as a strength of the Dirac delta function, and that strength is equal to the amount of discontinuity. Okay, so amount of discontinuity is 1, but because signal is jumping in negative direction, we will have a strength of -1, and this would be our derivative of the signal, the rectangular function x of t. Okay, so we have Dirac deltas at t equal to 0 and t equal to t naught. Okay, in this way we can plot the derivative of Dirac delta, derivative of rectangular function. Okay, so next let us try to understand how do we integrate the rectangular function. Okay, so for any signal x of t, so integral is defined as y of t is equal to integral minus infinity to t x of tau d tau. Okay, we call this as a running integral. Okay, so we call this fellow as a running integral. Okay, so we need any for a signal x of t, the integral is defined like this: integral minus infinity to t x of tau d tau. Now because the integral is with respect to tau, the first step would be like we have to convert everything into tau domain, and hence let us redraw the plot here with respect to tau domain. Okay, so plot remains same, but only the domain changes, and hence the plot would look like this. Okay, and we call this function as not x of t, now it has x of tau. Okay, now we are interested in evaluating y of t for all values of t. So t varies from, usually any signal varies, for any signal t varies from minus infinity to plus infinity. Okay, so our t starts at minus infinity. So what can we say? So first case we take when t is less than 0. So what will happen to our y of t? Okay, so let's assume t is less than 0. So we have to integrate from minus infinity to t. Okay, so we have to integrate from sorry for that. So we have to integrate from minus infinity to t, and t is less than 0. Because we don't have any signal in that range, we say that our y of t equal to 0. Okay, now in the second case, let's assume t lies between 0 and t naught. Okay, so if t lies between 0 and t naught, so how does that look? So my t is somewhere here. So t lies between 0 and t naught. So if you integrate from minus infinity to t, so our y of t would be in this fashion. Okay, so integral limits will be from minus infinity to t, but our signal exists only from 0 to t, and hence you will get integral 0 to t 1 d tau, which would be equal to t. Okay, so as a third case, what happens if t is greater than or equal to t naught? Okay, so in this case the region will look like this. So our t is greater than t naught. So if you try to integrate from minus infinity to t, our y of t would be equal to integral, because actually we should integrate from minus infinity to t, but as our signal exists only from 0 to t naught, it is enough that we integrate from 0 to t naught 1 d tau. So this would be equal to t naught. Okay, so as we have covered our complete t from minus infinity to infinity, we can try to evaluate, we can try to plot our function y of t. So let us summarize what we have got. So we have got y of t to be t naught for t greater than or equal to t naught. It is t for 0 less than or equal to t less than t naught, and this is 0 when t is less than 0. So if you plot this function, the plot will look like this. Okay, so the function starts at 0. So from 0 to t naught it is a straight line. Okay, so 0 to t naught it is a straight line whose equation is t, and from t naught to infinity its value is t naught. Okay, so this would be the integral of the rectangular function which is given here. So hopefully this problem helps you in understanding the derivative and integral of a rectangular function. Thank you.